Okay, hey, I got a good question here for number 28. And so I'm looking at it. I see it says a review problem. It could be approached in different ways, but I'm going to approach it, I think, as the author wants because he calls it a review problem. So let me explain. Let me go back to Physics 121 here. Your author and even uses a phrase, the elevator, because this idea was thought out by Einstein. It's referred to Einstein's elevator, and it's also called the equivalence principle. But Einstein was thinking about somebody in an elevator, and it would be a cable, maybe pulling them up or letting it down. But let's start here by saying the elevator is going up. And Einstein was thinking about this, and he said, okay, now if you add up all the forces in the vertical direction and set that equal to ma, so forces in the vertical direction give you acceleration in the vertical. And I'm only going to deal with the vertical, so I'll just drop the subscript y. But as I draw a free body diagram for this individual in the elevator, the bottom of the elevator is pushing up with a normal force. And of course, gravity is pushing down with weight, mg. And that's all the forces on there. The way I like to describe when you're doing a free body diagram is look for the force of gravity plus everything touching the object, which I'll just call this the person, the object. Now here's Einstein's thinking, and this is, I think, why it's called a review, and I think this is why the author used the elevator here, or at least part, because it looks like he uses a truck in part C. But the thinking of Einstein is this. Let's say you're just stationary, okay? And so, you're standing on the elevator, maybe the door's open, and you're letting people in and out, but you're just stationary there. Okay, so what would that mean if I added up all the forces? Okay, so up is the normal force, and down is mg. That's what I get from my free body diagram. And that has to equal to ma. But now remember, you're just standing there, so acceleration would be 0. And so this says your normal force is mg. Okay, but I'll call that scenario 1. Let's look at scenario 2. Now, scenario 2, let's say you're already in the elevator, the doors are closed, and you're beginning to speed up, and especially if there's a big tall building. If you've ever been those in express elevators, they accelerate up for a couple of floors, and they get to some speed, and they just keep going to that speed for 90 floors. So you get to the 90th floor kind of quickly. Okay, so let's say you're in the part at the beginning where the elevator is actually accelerating. So you wouldn't have it equal to 0. You would have something that looked like this. You would still have the same forces on you, which would then equal to ma. And of course, ma is upward. It is positive. So you would say that your normal force is mg plus ma. Now, this is where the equivalence principle was coined by Einstein. He looks at this and says, no, wait a minute. It kind of makes sense that as you are going up, the amount of force from the elevator is pushing up. So what you feel on your legs, or if there was actually a scale under your feet, what would read on that scale would be not just your weight, but its weight plus a little bit more. This little bit more is because of this upward acceleration. And so the scale would read more, or you would feel heavier. And so as it is pulling you up, you kind of feel something different. You feel a little bit heavier. And likewise, if the elevator was accelerating downward, so then A would be a negative number. So then it would be your weight minus a little bit. And so the normal force would be a little bit less. Your legs would feel less of a force. If there was a scale under you, you would read something less. Because the scale's reading that force between your legs and the ground. That's the normal force. And so Einstein kind of thought of it this way, that an upward acceleration or downward acceleration is the equivalent of a gravitational force. And that's where he uses the phrase the equivalence principle. So it doesn't really matter whether your acceleration is what I might call a true acceleration or the effect of gravity. They're equivalent. And so his argument goes, something like this. If you find yourself in a spaceship, then with no windows or no doors, so you can't really see out, and you put yourself or somebody else in the rocket ship, if this rocket ship was just sitting on the Earth, nothing exciting going on, no rocket fuel being burnt, you're just in there, just a closed up room, so you can't look out, you can't tell really if you're moving or not, but you would be able to feel this downward force. And of course, without any acceleration, it would just be mg, and you would, it would just be your weight. And if you were standing on a scale, it would just read your normal weight. You wouldn't think much about it. But on the other hand, if the spaceship was way out in outer space, so far away from the Earth that we don't have this term, but it's accelerating, and let's just say it's accelerating with 1g, then the rocket ship's actually accelerating, but you wouldn't be able to tell the difference. All you would do is feel that same force. You don't have any windows, you can't really tell anything, and so the argument here is that these are equivalent, whether it's a legitimate, I'll call it a legitimate acceleration, or where it's the effect of gravity. It's still a tug on you, and you don't know the difference. That's why, of course, many people propose on these long-distance travels, say if we ever make it to Mars or further, you're going to be on a rocket ship, and, to make people feel comfortable like they're at home, you just have an acceleration, and as long as you have enough fuel, you just keep accelerating at 1g or less. Usually the 0.8 is kind of the value that people talk about, because it would be nice if things weren't quite so heavy, but yet our body needs to function with a little bit of g, and we need that force ground, downward, just to make friction, say, between our shoes and the ground so we can walk, instead of just free floating. So this would be kind of an artificial gravity. You don't have a g, but you have an a instead. And if you're closed up with no windows or no doors, you wouldn't notice the difference. And so a lot of these ideas are that, send a rocket ship across space like this. When you get to the halfway point, you flip the rocket ship around. And as you approach your destination, your planet, so you left Earth here. So the first half of the trip, you've accelerated, got going real fast. And the second half, you deaccelerate. But you always have an acceleration away from the ground. And so if it's always 0.8, then you always feel like you're on a gravitational Earth. Well, I'm probably going too far down the road of the equivalence principle. But I'm sure that's why the author here calls this a review, because knowing then that a real acceleration and a g are kind of the same and they can be combined. In fact, I probably should have wrote this equation as mg plus a. If we just combine the two accelerations together, and of course remember they're vectors, so we got the plus and minus, and we also have right angles, and that's where this problem is going to come into play. We can just do the equivalence. So let me do that. Let me not try to solve the whole pendulum problem again. In fact, this thing asks for a simple pendulum of 5 meters long. What is the period of oscillation if it is located on an elevator that is accelerating up at 5? So let me call this, for lack of better symbol, G. Well, let's call it G total. I won't go with prime. Kind of looks like a derivative. But G total would be adding the two vectors together. And so normally I would, be upward. I guess I would just get this. It would be, and I kind of already did it, a G plus an A. So if you're going upward, those are both positive. And vectors are easy when they're same direction. You just add them. So it's 9.8 from the normal gravity, and then it's plus another 5. And so the total of this, 9.8 plus, I guess I don't need a calculator for that, 14.8 meters per second squared is the total G. And this is where the equivalent principle would come into play. We figured out that the period of a pendulum is 2 pi times the square root of L over G. Okay? And that, of course, is what we worked out on the Earth. But G was just a symbol. That was the acceleration. And so you could actually then change this to what you might call the total effect using the equivalence principle. That it would be the g from the Earth plus the acceleration of whatever you're in. And so in this case, it would just be 2 pi over the square root of 5 over something on my paper here. Okay. 2 pi, the square root of length 5, and g then would be this 14.8. So if we were on, say, a planet that had a higher acceleration, just 14.9, I mean, we would have done exactly the same thing. And that's what this is equivalent to. If we're in this elevator going up with this in acceleration, it's the equivalent of being on a planet with an acceleration of 14.8. So if I go 5 divided by 14.8 and then take the square roots of that and then multiply by a 2 pi, I would get the period, so 3.65. Whereas B's, again, same logic, and it's requiring you to go back and look at the equivalence principle. So this one, it's going down, I believe. Maybe I better read it. What is the period of an elevator if the elevator is accelerating downward? So this would just be a -5, and I'll just do the same thing. The equivalent g, the total g, in this case would be the 9.8. You might say plus a -5 meters per second squared. And so we would have 4.8 meters per second squared. And so, again, the equivalent principle, well, 4.8, it doesn't really matter if this is like a smaller planet and we just have less of an acceleration, or it doesn't really matter if we have no planet and we are just in a rocket ship accelerating with that. Or in this case, it's a combination of the planet and the acceleration of the object we're in. They are equivalent to each other. So we wouldn't need to go through and rederive anything. The derivation would be the same if we were on this small planet. So this would be its length, 5, divided by the acceleration of 4.8. So 5 divided by 4.8, square root, multiplied by 2, and multiplied by pi. And so the period is quite a bit bigger. It is 6.41 seconds. And I guess I should have put seconds up here. And it makes sense because we have less of an acceleration. We have less of a tug for this pendulum swinging back and forth. In fact, you could even imagine that if the whole elevator was just falling, it was in free fall, that it would never swing. The pendulum, if you pulled to one side and the whole elevator fell, the thing would just be stuck there. You'd be in free fall, and the thing would be just moving down, and the period would be infinite, if you will. It never did swing. And of course, you'd put a 0 down here, which would make a calculation of an infinite, and so it would take an infinite amount of time before this thing swung. Which finally brings me to the last one. Maybe it's a little harder to do, but the equivalent or the total, since they're at right angles, is really the key. And so I'll just remind you from your Physics 121, if you had, this vector has length A and this vector has length B, the total of those two would be the a squared b squared square root, right? That's the Pythagorean's theorem. That's a terrible straight line. But that's the Pythagorean's theorem to explain the total. So in this case, I will take the 9.8 and square it, because that would be the downward acceleration. And in this one, since we're moving sideways, it says, hey, you're in this truck moving with an acceleration of 5. It would be 5 squared, and then take the square root. So I'm really combining the two, but at right angles. So we call this addition and quadrature, not just a simple addition that you're learned in second grade, but the addition of two things at right angles to each other. So in a quadrant, if you will. So quadrature. So this is equivalent to 9.8, and we'll go squared, plus 5 squared, and then the square root of all of this gives me an equivalence of 11. And it would actually be 11 at an angle, right? Because we would have, 9.8 down and 5 over, and so the equivalence would be that way. But, well, it's probably best to draw it that way, so that if you kind of imagine yourself in a big truck, something hanging from the ceiling, it would swing like that, and so the pendulum would go back and forth with the period we're about to calculate, but then based up on a center line at an angle as the two vectors, are added together. All right, so again, I'm going to take advantage of the equivalence principle to solve most of this. Okay, so the length is still 5, but now the total acceleration is 11. And so grabbing the calculator, I've got 5 divided by 11, taking the square root of that, times a 2 and a pi, gives me a period of 4.24 seconds. So there you have it, and it's really all based upon the equivalence principle. So start with the solution we already did just with a simple g, and then realize we can more generalize that. And that g would work if we went to, say, the moon. It would just be a different value. And then likewise with the equivalence principle, a different value of g would be true if you were an accelerating object. So up, down, and even sideways. With sideways, we got to kind of write it in quadrature. All right, hope that helped.